You have you're on a PC?
I'm on Mac. I have the buttons at the bottom. I got the
So,
eye in the
yep.
top left-hand corner.
Probably your full screen, I would imagine. So if you go up and sort of highlight over where the menu buttons would be, so you'll see something that says WebEx, File, Edit, Share, View, Audio, Participant, Meeting, Window, and Help.
Yes, sir.
Yeah, so next to Edit, there should be something that says Share. Do you see that?
Or Tyler, can you do it? If he can't share it. Should be in there.
You are the presenter. I just need.
No, sir. I'm trying to see what's.
Were you able to find it?
We are still trying to figure out, Dr. Marco.
Okay, Dr. Khan. I think Shift Command K allows you to share.
Shift Command K.
Yeah, so Shift Command and then K simultaneously.
Is it Mac?
Yes, sir.
Yeah, he has a Mac, so that's why I think.
Okay, so maybe Control Command K.
Tyler might be able to do it.
I think you still are the host, so probably doesn't have the host.
I made him the host.
Oh, you did?
Yeah.
Yeah, it's asking for a host.
Maybe you're the host when I click on it.
Okay, but I passed you the ball. Okay, do we have a backup on the sharing? Tyler?
Yeah, I'm working on it.
Go
Okay.
ahead and share.
Yeah, I'm working on it.
Okay.
Thank you, Alex.
Yeah, right next to this, you may see. There's gonna be like 4 rings there. 3 rings, or 3, yeah. 3 rings upstairs for people like watching. No, Tim has Tim on them.
Oh, Tim has it?
Yeah. What's that? I do, they're right here. I think I'm making progress.
Hey, Mike, you need to get on mute.
I'm sharing.
Okay, so somebody share. We see a screen. Again, a gentle reminder.
Mike was asking me, did you get the cover thing printed out and stuff? There's
Boom, solve that problem. I have the power to mute people. So I think,
Oops, Tyler.
okay, can everybody see the screen now?
Yes.
Perfect, thank you. You're all muted, great. It's a trick question.
All right. Good morning, everyone. I'm John Knobloch. I'm representing Clemson as part of Team Storm. We're here to present our preliminary design review. This is how our team structure lays out who is in charge of what from top to bottom. So after reviewing the MCR, we went back to the feedback that we got and determined what was necessary to make changes and what we should implement. Some of these were the integration, creating an integration lead. We established that with Andy Person, who's also our manufacturing lead, and we felt like that was a good implementation of both those subject areas. The other big thing that we just did was the water filtration. We heard feedback about how did we establish our payload and what was the most important thing to get to distressed people in situations, and we determined that drinkable water is very important, and is also some of the hardest things to get to. So the next slide shows examples of recent events where STORM would excel in getting and achieving our goal of identifying and providing aid to distressed people. This slide shows our mission profile, where we will insert the payload into the UAS, climb to our cruise altitude via either hand launch or vertical takeoff, and then fly to the target area at 35 miles an hour, and then descend to a lower height to survey and drop the payload. And then once the mission is complete, reascend, fly back to base, and descend and land. Our mission and design requirements consist of a minimum flight time of 60 minutes, a cruise speed of 35 miles an hour, stretch goals of VTOL capabilities and payload drop, along with an H-tail to help with the VTOL stabilization and belly landing due to the payload drop. Our configuration selection and justification, we established that due to our payload drop goal, we wanted a high wing configuration. That was also to add the benefit of increased roll stability. The H-tail was important to help, like I said earlier, to establish stability due to the VTOL, and we decided to use flaperons to help increase our stability as well. This is our concept. On the left, we have our OpenVSP model, and on the right, we have our 3DE model. As you can see on the OpenVSP model, we have 4 vertical propellers to achieve vertical takeoff. And on 3DE, we are working on establishing the best route to implement these vertical propellers. The UAS sizing is a 2-foot length fuselage and an 8-inch width, wingspan of 96 inches, wing root of 11 inches, and a 9-inch record length for 9 inches. For the empennage, for the payload, we are including a Lifeline small first aid kit. It's got a hard shell case, and it's got 30-piece emergency first aid kit, and it contains an emergency whistle. As I mentioned earlier, the life straw, and a qubit GPS tracker. This is important because not only does it allow for GPS tracking if the distressed people were to move, but it also allows two-way communication. This is important because if the people that are saved are distressed, we can establish, do they need specific medical capabilities, such as sugar for diabetes or anything else that could be that we don't know before. This shows what our payload looks like. It's a simplified picture of it. It has our dimensions and our weight. It is approximately 3/4 of a pound and about $90 per payload. This shows how our payload will be held in our fuselage. The fuselage will hold 2 payloads, and it'll be held symmetrically so that it will not influence the CG as badly when one is dropped. This is how we are going to release our payloads. It's a serverless payload release. It's triggered remotely. This also has the ability to be 3D printed. The release mechanism, the released part, not the release mechanism, has the ability to be 3D printed. And it's only $25, with the release plate is only being $3.50 to replace per time. So now I'm going to hand it over to Prince.
Andy. Sorry. Okay.
Andy.
Here is our constraint and sizing analysis for the over wing loading and power loading. So here we have a W over S set at about 79 to get a CL or a CL max of 1.6. And this is where we basically got all our criteria for max speed, takeoff velocity, power loading, and wing sizing. So next slide, please. So here is our airfoil selection. So we had a wide base of airfoils, but after analysis, we broke it down to these 5 airfoils. So the airfoils that we have selected for testing was the SD7062, the NACA 6412, the NACA 6410, the CR 001, and then the Epler E212. We had a CL max minimal 1.4. We were looking for high lift over drag ratios, and we ran on X-Foil and X-Flyer with a Reynolds number of about 100,000. So the first graph here is our CL over CD graph. So basically for this graph, it shows the coefficient of drag the airfoil makes for a given coefficient of lift. And you want your drag to be low as possible for your given lift range. So you want it to be furthest to the left between CL1 to 1.5. And then the next graph is our CO versus alpha. Oh, the Q. Yeah, that next graph is the CO versus alpha graph, and here's just our coefficient of lift. Coefficient of lift is heavily dependent upon the shape of the airfoil. So our CL max requirement was 1.4. So we basically looked at whichever airfoil meets our CL max requirement was a viable option for our airfoil selection. This is our lift over drag ratio graph, and basically an airfoil with a high lift over drag ratio produces a large amount of lift and a small amount of drag, and it's an indication of our aerodynamic efficiency. So as you can see, the CR 001 has the highest L over D, followed by the Epler E212, but the SD7062 has it's high, but it's spread out for a larger angle of alpha. So next graph. So here, after looking at everything from alpha, CL over alpha to CL over CD, we chose the SD7062. It has a wider CL over CD curve. It stalls at a higher angle of attack, and it has a high CL over CD max lift over drag ratio. Its thickness is 14%. The thickness position is at 27.29%, and has a camber of about 4%. And the maximum camber position is at 38%. And the CL max value that it gives is 1.56, which meets our requirement for 1.4. So here are our VN diagrams. The first VN diagram to the left is for normal flight. So that's just regular flaps. And as you can see, there's our gust lines. Our VC is our basically it sits within our gust lines. And then for the full flaps, that is the VN diagram for our full flaps. Next graph, please. And
All
here,
right.
this is an aerodynamic analysis. Here, I will hand it over to him.
Thanks, Prince. So for our aerodynamic analysis, we use the AVL interface provided on Valmus to make an AVL file. And we ran the analysis to get our stability derivatives, get more accurate values for CL max, and then to trim the aircraft. What we noticed most using AVL was that our CL max dropped to 1.41 with no flaps. However, with the addition of flaps, we received a CL max of 2.39, which is definitely an overestimate. But it shows that our CL max will increase dramatically, which will allow us to be able to hand launch the aircraft and it not just fall into the ground right off takeoff. For our weight and balance, we found the CG using approximate weight values for each component and then solving a simple statics problem. The values for CL alpha, CM alpha, CL beta, and CN beta all are shown to show that we have a stable aircraft, and a static margin of 24.02% was found. We're anticipating that estimated weight values are going to vary and that the CG is going to move. So we have a 2-inch margin for our CG to move backwards until our aircraft becomes unstable and our static margin goes below 0. So we did a trade study to see how the battery weights affected loiter time. Using a 5,000 milliamp hour 14.8 volt battery. All of the asymptotes at 1.1, 2.2, 3.3, and 4.4 represent a battery. So the low line would be 1, then 2, then 3, then 4. We want to maximize our power usage out of a battery. So if we have 3 batteries, then we would want to, then we can get a flight time of up to 1.5 hours using, if our structure, if our empty weight to takeoff rate ratio is up to 0.45, so we have margin to not, if we don't design our structure efficiently enough, there is some leeway there. Our second trade study was done on wing loading. We were trying to figure out the best wing area to design our UAS to. The lower the wing loading, the higher the wing loading, the harder it is the higher our takeoff velocity needed to be. So in order to get a compromise of a lower wing loading to be able to hand launch the aircraft, but also not to have a CL that is to also increase our CL, we had to find a mid-range, which ended up being between 6 feet to around 7 feet of wing area. The weight and power analysis spreadsheet was used off of Valmus to get numbers. We inputted values of CL max of 2.1, assuming a loiter time of 1 hour and 15 minutes, cruising at 35 miles per hour, and having a wing area of 6.67 feet. The highlighted cells show the numbers that we are expecting to be around. Our V takeoff is around 20 miles per hour, which may seem high. However, a human can run about 13 miles an hour, and then being able to throw the UAS as well as the distance that it can travel down from being hand launched, we would be able to make this takeoff velocity. So for our polar motor on the nose, we were planning on using a Tiger motor, 490 kilovolt motor. This motor has a low KV, and we would put a large 18 by 6 inch prop on the front of it to have low RPMs but maintain the same amount of thrust, which would increase the efficiency of our propulsion system and allow us to have a longer flight time. The quad motors for our VTOL, we were looking at using a Turnigy 790 kilovolt brushless outrigger motor. We would need 4 of these, so each one with the propellers creates about 3.64 pounds of thrust. Multiplied by 4, we end up getting right around 15 pounds of thrust. Our thrust to rate ratio of 1.4, if we had the aircraft, would be 10 pounds. So we would have enough thrust in order to take off and use VTOL capabilities. The propellers we were looking at using a foldable carbon fiber propeller on the front, so that on belly landings we aren't breaking propellers off. Initially, we would be considered using a non-carbon fiber plastic propeller just to keep costs down. And then for our propellers on our VTOL, on the 4 motors for VTOL, using 11 by 4.7 motors, and so that we can get enough thrust to actually take off vertically. The speed controller is a 80 amp speed controller that will allow us that'll take care of all the power to be running through it. It's a little bit of overkill considering our motor only has a peak amperage of 60 amps. So we have margin for built in with our speed controller as well. For our controls, this is an overview of our control system that will be implemented. We're going to use a Pixhawk 4 that's connected to the ground control and then the radio control to manually control the UAS. Also on board the aircraft, we'll have a Navio 2 and a Raspberry Pi 3 and a Pi Cam to take care of human detection while we are flying. The Navio 2 the Raspberry Pi will take information off of the Pi camera and process the information. And the Navio 2 will then send information to the motors and ailerons to control the aircraft to go back to the human on the ground to be able to drop our payload. Hardware for controls, we use a Pixhawk 4, a Raspberry Pi 3, plus a Navio 2, a Raspberry Pi camera board, and then a Taranis X9D Plus for our transmitter. Additional hardware would be a GPS system, a differential airspeed sensors so we can see how fast we are flying, as well as LiDAR to be able to tell how far we are off the ground. And the autonomous parts of our aircraft have human and obstacle detection, payload dropping, being able to drop a payload at an appropriate height, as well as being able to survey areas with the desired flight path, and stability control built into our control system to control against strong gusts, and be able to land the system autonomously, as well as being able to transfer from autonomous flight to manual control flight by an operator. I'm going to send it back over to Prince for the risk assessment.
So for risk assessment, we looked at 4 things: safety, cost, schedule, and technical. For safety, it was UAS hand launching, battery type. For cost, shipping costs, and basically not to go over budget. Scheduling, we have different spring break conflicts. So our Tuskegee is March 2nd through the 10th, and Clemson and Georgia Tech is the 16th through the 24th. So coordinating between those breaks before and after. And then for technical, we have a big emphasis on VTOL. So our competency for VTOL, propeller failure, and our payload drop, it would change the CG. So making sure that our payload drop doesn't affect our flight, and the parachute that would be coming with the payload, if it would deploy or not, and our position of CG relative to our neutral point, and our failures or our flaperons to help with our takeoff. So here is a basic budget schedule. This is an estimate. So for propulsion, as you can see, we have about $550. Controls is $530. Payload is $200. Our structures is $1,500. And that leaves us with a total of $2,780 from our budget. And this is how much we have remaining, which is $3,220. And that's just the estimate, just give or take. So here is a color coordinated Gantt chart. This just shows when things are due throughout the semester. And if you go to the next slide, this is a more detailed Gantt chart. It shows how many days we have to complete it from the start date, and it shows us what phases we're in for the Gantt chart. So in conclusion, we showed in what circumstances our UAS would be beneficial. We displayed our plan for implementing our UAS with multiple design applications, how our payload would be released and packaged, the mobility of our UAS, and the ability to locate survivors. We determined our propulsion system, and we gave margins and representations with graphs and calculations to show thoroughly how we are designing our UAS to handle all our aerodynamic circumstances. So this is just a side note. We didn't really put this in the main PowerPoint, but this is the weight, dimensions, and cost for our payload, everything that's in our payload. This is more detailed with the actual dimensions and actual weight. So we just wanted to throw this in at the end.
We will now be open for questions.
Branko Lakic speaking from Boeing. I actually had to drop off for a couple of minutes, and I think I missed a key part of the presentation about the architecture of and the airplane configuration selection. But I kind of gathered that you opted for a fuselage with a propeller at the nose and horizontal tail with 2 vertical tails, which, if that is the case, I'm a little confused how is that conducive to the actual mission, surveillance and payload release, because, if you are looking for survivors, your equipment, surveillance equipment should be in the probably unobstructed area of the airplane, which kind of implicates a forward fuselage or the nose possibly. And that would kind of drive the propulsion unit to the back of the fuselage, and because you are releasing the payload, again, the payload should be centrally located around CG in order not to affect your balance during the flight. So I really like your concept of a very simple latch payload release. It's simple as it can, probably very weight efficient, which is allowing you to maximize your payload. I'm a little confused why you choose the 2 vertical tails rather than maybe just a V-tail configuration, which I believe is more weight efficient. And then one thing that I didn't gather is the mission planned to be carried in the night, and do you have an infrared capability in your camera?
So can we go back to the slide, whoever's presenting, can you go back to the slide with the CAD models? One of the biggest reasons that we chose an H-tail, and it's not reflected in the CAD models yet since they're very preliminary, but we might attach the booms that have the propellers on them to the empennage so that we can have a more stable tail. Also, in terms of the camera system, while we do have a puller nose in the front, we were planning to have some sort of either cutout or plastic dome that the camera could see out of below the nose, because having the camera in the very tip of the nose would not be very effective either in terms of surveillance, because you will only catch a very small part of the land area, and it makes more sense to have it angled downward. So we were planning to try to fit it underneath, although if that does not work, we could consider putting it in the back. But again, another problem with having the propeller in the back would be with the payload drop, because we don't want to drop the payload into the propeller.
And then to talk about the H-tail as well, if you go to the slide, it talks about the configuration selection justification. In order to meet the easily transportable requirement, the H-tail gives us the same amount of surface area on the vertical stabilizer as just one large vertical stabilizer, and we can break those down into 2 smaller so that we can, when transporting the UAS, we will be able to put it into a smaller space.
Yeah, it makes perfect sense. I concur that, maybe switching to the 2 tail booms for this particular mission may make a lot of sense. Also, if you check on the internet, you're going to find various sites that are selling a clear plastic spheres in the different diameters. I actually found a few, and you can definitely buy off the shelf really inexpensively an in-facing sphere for the nose and the camera. And yes, you're right, you do not put the camera in the tip of the nose. It has to be angled down and forward. As long as you have the largest possible angle of unobstructed view, that is the imperative of the mission. So I agree with where you're going with it.
Thank you.
Any further questions?
Does the camera do infrared?
This camera does not. However, we've looked at other ones. The control system that we lined up, or that we presented here, has a built-in computer vision processing software, which is one of the benefits of using the Raspberry Pi camera. However, we have looked at the potential of using infrared cameras, although most detection will probably be done during the day, reducing the need for infrared.
So we are also using a LiDAR detection so that we are not dependent on the light source for detection of the surroundings.
All right, if there's no further questions, thank you for letting us present today.
Great questions. We're